Now the speech. Now for the rest, the speech is given by Dharm, and I invite Girija to chair the session.
Okay, so we welcome everybody after tea and from Veer, and he will say something about Green-Lazarsfeld NP property NP for Hibi rings.
Hi, so am I audible? Yeah, so today I will talk about Green-Lazarsfeld property NP for Hibi rings. So my talk is divided into 3 sections. So first I'll define what Green-Lazarsfeld property NP is. Then I'll define what Hibi rings are, and at last I'll discuss Green-Lazarsfeld property NP for several product of Hibi rings. So let's set up some notations first. Yeah, so let A be a field, and throughout this talk A will be a field, and let S be a standard graded polynomial ring over A in n variables. So by standard graded we mean the degree of the variables is 1. I mean for all variables x1 to xn is 1. And if we set the degree of all variables to be 1, then one can write SS in the following form: the direction and SI where I greater than equals to 0. So here SI is the K vector space generated by degree I monomials of S, and let M be the graded maximum ideal of S, and furthermore, let I be a graded S ideal. So S mod I will be a graded K algebra, and also S mod I has a S module structure, and let F be the graded minimal resolution of S mod I over S. So what we mean by this term graded minimal resolution? So let's try to understand this. So by free resolution, we mean that all these modules Fi's are free S modules, and F is a exact complex. And furthermore, the co-kernel of the map Phi1 is S mod I. And by graded free resolution, we mean F should be a free resolution, plus the module Fi's are graded free S modules, and the map Phi's are homogeneous maps of degree 0. So what we mean by homogeneous map of degree 0, that means under the map Phi, some element of degree B should map to a element of degree B. And at last, by minimal free resolution, we mean that F should be a free resolution, plus under the map Phi, the image of F, the free module Fi should be contained inside M times F of I minus 1. Right? Okay. So one remark here. So since we are taking the minimal resolution of S mod, graded minimal resolution of S mod I over S. So all these module Fi's are module of finite rank. So if we fix the basis for all the modules Fi and let F be the graded minimal resolution of S mod I over S, then the entries in the matrices Phi's are either zeros or homogeneous polynomial of positive degree. All right. So now we have enough notations to define what Green-Lazarsfeld property NP is. So let P be a natural number, and under the notations defined above, that means S is a standard graded polynomial ring, I is a graded S ideal, and F is the graded minimal resolution of S mod I over S. We say that S mod I satisfies Green-Lazarsfeld property NP if the ring S mod I is a normal ring, and the module Fi where I is between 1 and P is direct sum of S of minus I minus 1. So what this module S of minus I minus 1 is? So let's define this. So for a J in nature N, the module S of minus J is isomorphic to S as an S module. It is a graded S module, and some degree D piece of this module is actually the degree J plus D piece of the graded module S. And so what we are actually essentially doing is we are just shifting the degrees of the module S over S only, right? And then we are looking at this particular module. And so as I stated earlier that Fi's are module of finite rank, So there will be some finitely many copies here only. I have not quantified that. I mean, yes.
It's a pure resolution, is it? I mean, that direction is over what? It's just copies of the same.
Yeah, it's just copies of the sum s of -1 and minus I minus 1 only.
In particular, it's a pure resolution.
Up to pth stage.
Oh, up to pH.
Up to pth stage. So that's what the property n creates.
Okay.
Right? Okay, so let's just elaborate this furthermore. Suppose S mod I satisfies Green-Lazarsfeld property NP, then F has the following form.
So in fact, linear up to NP.
Yeah, linear up to NP. Yeah, right. So S, I mean, since we are taking resolution of S mod I, S will be actually F0 will be S, and if we plug in I is equals to 1, we have shift of -2 here only, right? And furthermore, up to P, we have shift of -3 -1. So until that particular stage, I mean pth position, the resolution is linear. Okay, and now let's try to understand it for some smaller values of P. So for P is equals to 1, S mod I should be normal, that is condition is always there. So we should have the shift of -2 here, right? And recall that the matrix T1 is a row matrix, and the entries here are the elements, the generating set of I. So we are essentially saying that the ideal I should be generated by quadrants. Plus here for P2, the entry, this matrix P2 is called the presentation matrix of the ideal I. And so if a ring satisfies N2 or NP for some higher piece, we are saying that the ideal I should be linearly presented. Alright, so now, okay, so now we proceed toward the definition of Hibi rings. So Hibi rings are algebraic objects, those are associated to some distributive lattices, finite distributive lattices. So before defining Hibi rings, we define some terms from poset theory only. So let P be a finite poset. A subset alpha of P is said to be an order ideal if for any x in alpha and y in P, with y is less than x in P, we have y belongs to alpha. That means if there is some element in alpha, then all elements below that particular element should also be in alpha. And for a poset P, let I of P be the set of all order ideals of P. Then the under operation of union and intersection, I of P forms a distributive lattice. And since P is a finite poset, so this will be a finite distributive lattice only. So one more definition. Let L be a finite lattice, and let X be an element X is said to be a joint reducible element if X is not the minimal element, and X cannot be written. If X can be written as join of two elements in L, then one of those two elements should be equals to X only. Right? Okay. So now let's use these two definitions and state the theorem of Birkhoff. So let L be a finite distributive lattice and P be a subposet of joint reducibles. Then L is isomorphic to I of P, and we have already observed that I of P is a distributive lattice, right? And we will use actually this definition, is this theorem of Birkhoff to define Hibi rings. So now I've defined everything for finite posets and finite distributive lattices only. So I'll just state a remark that throughout this talk, all posets and distributive lattices will be actually finite posets or distributive lattices. Okay, now let's proceed toward the definition of Hibi ring. That L is equal to I of P a distributive lattice, where P is the poset on the set P1 up to Pn. And let R be a polynomial ring and n plus 1 variables, where n is the cardinality of the poset P. So now recall that an element of L is actually order ideal of P, and order ideal of P are subset of P only, right? So for an element L, define a monomial U alpha in R, where R is this polynomial ring, defined as follows. It's P into the product of the variable Zi if Pi belongs to alpha. If Pi is in alpha, we are taking Zi there, and then we are taking the product of that. And let RL be the subring of R generated by these monomials. This ring RL is called the Hibi ring associated to L. Okay, now let's take an example and try to understand whatever we have defined so far in poset theory and Hibi ring. So let's take this poset P. Observe that the singleton P1 is an order ideal there. Similarly P2, similarly P2, P4, because for below P4 there is only one element P2 that is in the subset. Similarly P1, P2, P4, and P1, P2, P3. Now remember that P1, P3 is not a order ideal because there is an element P2 below P3 that is not in P1, P3, right? And if you look at this distributive lattice, then the joint reducible elements here are P1, P2, P2, P4, and P1, P2, P3. And if we look at the subposet of these particular joint reducibles, it's actually isomorphic to P only. So this verifies Birkhoff's theorem. Okay, now how the Hibi ring is defined? So given this monomial, order ideal Pi, we have the monomial TZ1, and associated with P1, P2, P4, we have TZ1, Z2, Z4. Associated to we have TZ1, Z2, Z3, Z4. We are taking all product of monomials here. All product of variables here because P contains all the elements there. And the Hibi ring R will be actually this. So this can be like seen from the figure easily. All right. So now let's take a polynomial ring in cardinality of L many variables, and we are quantifying the variables with the elements of L only. Let phi be a K algebra map from Ki to Rl, defined by X alpha maps to U alpha. So one can easily see that this map is a surjective map, surjective K algebra map, and the kernel of this map is generated by quadratics of the following form, where X alpha times X beta minus X alpha join beta, X alpha meet beta, where alpha beta belongs to L and alpha beta are incomparable elements. So by incomparable we mean neither alpha is less than beta nor beta is less than alpha. So let's go back to the figure. Okay, so in this figure, P1 and P2, P4 are two incomparable elements, right? And corresponding to this, the generator will be of the kernel will be X P1, X P2, P4, and the union of these two, that is X P1, P2, P4 into the joint meet of these two elements, that is X empty set, right? And similar way, one can write all the generators of the kernel. And this ideal actually called Hibi ideal. Okay, I'll not go into the definition. Okay, so the Hibi rings were defined by Takayuki Hibi in his paper of 1987, and in that introductory paper, he proved that Hibi rings are normal Cohen-Macaulay domain of dimension cardinality of P plus 1. So here dimension is the full dimension, right? Okay, so observe that Hibi rings are normal, and the defining ideal is generated by quadrats. So Hibi ring satisfies property N1. And now we will study property NP for some hierarchies. So before that, so let me state, I want to define the standard product of two Hibi rings. So before that, I'll state some definition from poset theory again. So let P and Q be two poset on disjoint sets. The disjoint union of the poset P and Q is the poset P plus Q on the set P union Q with the following order. If xy belongs to P plus Q, then x is less than y. If either xy belongs to P and x is less than y in P, or xy belongs to Q and x is less than y in Q, right? So any two elements, any element of P will be incomparable to any element of Q. And if a poset can be written as disjoint union of two posets, we call that poset disconnected. Otherwise, we say that so this type of we say that the poset is connected. Let's see an example. In the figure A, the poset is connected, but in the figure B, the poset is disconnected. So in other words, a poset can be seen as from the Hesse diagram of that particular poset. If the Hesse diagram is connected, then the poset is connected. If the Hesse diagram is disconnected, then the poset is disconnected. Right. So now what second product is, so let A and B be two graded K algebras. Then the second product of A and B is a graded K algebra denoted by A star B, such that the ith copy of that is AI tensor BI. So observe that AI and BI are two K vector spaces, and we are taking the tensor of them over K, and then we are taking direct measure for all I. And now so one fact, let P1 and P2 be two posets, P be the disjoint union. Then the ring R of IP is isomorphic to the second product of column of the Hibi rings R of IP1 and R of IP2. So second product of two Hibi rings is again a Hibi ring. And one more fact, so let P be a poset, then P is a chain if and only if R of IP is a polynomial ring. So by chain we mean that P is a totally ordered poset, right? Okay, so now some observations from here. Hibi rings can be viewed as a polynomial ring. Polynomial rings can be viewed as a Hibi ring. First, the second product of two Hibi ring is again a Hibi ring. So second product of two polynomial ring can be viewed as a Hibi ring also. And thus Green-Lazarsfeld property NP for this second product of polynomial ring has been studied by various authors, and it is actually completely studied. So let recall all the results about the Green-Lazarsfeld property for second product of polynomial rings. Let A be a second product of R polynomial ring, such that in each polynomial ring there are at least two variables. So Sarke proved that if R is equals to 2, then A satisfies property N2. That means if you take second product of two polynomial rings, then the ring satisfies the property N2. And for R is equals to 2 only, Lazarov and Pragasian and Weyman proved that A satisfies property N3 if K contains the field Q. And Hashimoto again, like for R is equal to show that if N1 and N2 are greater than 4 and the characteristic of the field is 3, then A does not satisfy property N3. So if N1 and N2 are greater than or equal to 4, that means in each polynomial ring there should be at least 5 variables. In that case, yeah, so the graded minimal resolution of second product of two polynomial rings, at least, yeah, depends on the characteristic of the field. And finally, Rube proved that if R is greater than or equal to 3 and the characteristic of the field is 0, then A satisfies property N3, but it does not satisfy property N4. And we were kind of generalizing the result of Rube, and we proved the following. Let P1 and P2, let P1 be a poset and P2 is a chain, and P be the disjoint union. If R of IP1 satisfies property N2, then so does R of IP. Okay, so what this theorem actually says is, if P2 is a chain, then recall that R of IP2 is a polynomial ring. So what we are, and R of IP is the second product of R of IP1 and R of IP2. So what we are proving is, if a Hibi ring satisfies property N2, then a second product with a polynomial ring in finitely many variables also satisfies property N2. And the similar statement we have for N3. So let P be a poset. If a Hibi ring satisfies property N3, then so does its second product with a polynomial ring in two variables. Well, recall that the result of Hashimoto says that if we take, suppose for example, R of IP is a polynomial ring in 5 variables, and if we take 5 variables here, then over field of characteristic 3, it does not satisfy property N3. So one cannot generalize this result for any polynomial ring here. All right. Furthermore, we prove the following: let P1 and P2 be two posets, and P be their disjoint union. If the ring R of IP satisfies property NP for some P, then so does the ring R of IP1 and R of IP2. And at last, we prove that, sorry, any question? Yeah. So at last, we prove that if a Hibi ring satisfies property N4, then it is a polynomial ring or it has a linear resolution. So by linear resolution, we mean it satisfies property NP for all P's. Yeah, so that's all from my side. Thank you. And here are the references I have used.
Thank you very much. Very nice talk. Any questions? Any questions?
Okay. So,
Yes.
your second product, polynomial ring. So is that the homogeneous coordinate ring of Veronese variety?
No, so if you take R is equal to 2, right, then it is actually a determinant ring of 2 cross 2 minus of a generative matrix. Okay. Yeah, in n variables. Yeah.
That's how that's to, because he
Yeah, right. Right. So
So
they have actually, yeah, sorry, I'll just go back here. Yeah, so in that, but for determinantal rings, they have actually studied the resolution, the whole resolution for over the
yes,
characteristic, zero fields.
correct.
Yeah, and as a consequence, we get that the ring satisfies property N3. Yeah, and similarly for Sharpe only, he also studied the determinantal ring, at least the property N2 for determinantal ring. Yeah. In fact, the term Green-Lazarsfeld property NP actually occurs in the paper of Green-Lazarsfeld of 1986, and one can check that these results are actually proved way before that. Yeah.
Check maybe online questions.
And Prakash and women were looking at,
Yes.
women looked at the symmetric and skew symmetric sort of, minors of a symmetric matrix or a symmetric matrix. So in what context what is it, Prakash?
Yeah, so they were actually taking, so take a generated matrix
Yeah.
of some n rows, n columns, and there's the xij is the value corresponding to ij position, right? Take like determinantal, take the determinantal id is identified by some r cross r minus of that, where r is between 2 to minimum of m and n. So there actually studies the resolution for the defining, I mean the idea defined by the r cross r minus in that case. So yeah.
But isn't that what Lasku did?
So okay, so I mean I have read somewhere that there was some issue in the last book paper, and they have actually rectified this. And so his paper is actually not in English, so I am not sure what the issue was, but I have read it in some paper that there was some issue, and they have rectified it, and yeah, so something like that.
Okay, so can you show that reference?
Yeah, sure.
And your first theorem sort of includes as a special case the
Of Rubin?
yeah, because see, for example, this thing,
Yeah.
if you take P1 itself to be a chain,
P2 to yeah, right. If you take
then
P1 to
wouldn't
be a
that
chain.
earlier thing be a follow as a special?
Yeah, right. In fact, if we take P1 to be union of chains,
Yeah.
right, then Rubin's result also follows from this one.
And what technique do you use?
Okay, so the technique is actually, so the proof of this theorem is actually motivated from the Rubin's proof only.
Which proof, sorry?
So Rubin's proof, Rubin, I mean, she proved the last one, right? Or if we take r greater than equal to 3, then yeah, right. So okay, so the proof follows as like, so one can see this Hibi rings as a semi-group rings, right? And for semi-group rings, one can, I mean, study the Betti numbers using the something called, I mean, at least Bruns and Harzot call them square-free divisor and the homologies of square-free divisor complexes. So one has to prove that, I mean, at least, yeah, for if we take, okay, sorry, so I may have to define some more things. So at least if we take some degree 4 element in the semi-group, right? And then there is a something called square-free divisor complex defined to each element in X. And for that, one has to prove that the first homology vanishes for all degree 4 elements. So this is actually the idea for proof of the theorem 1, right? And this is actually the same idea, but Rubin did, I mean, improving her results.
Your work is published.
No, it's a preprint. Yeah, it's not archive. It's a preprint. Yeah. So
looks like no more questions from online people. Thanks very much.
Sorry for the introduction, sir.
That's fine.
Yeah. It is online, but it is
Actually, next is the plenary, no?
yeah.
Yeah.
It is online. Then we can have to
But maybe people from other
yeah, so we-